Okay. So what was Einstein's explanation for this that classical physics could not explain? So the genius of Einstein was that he saw the explanation by combining Planck's idea of quantization of light to these photoelectrons that are emitted. And he said that Einstein extended Planck's idea of quantization to light and said a tiny packet of light energy is emitted when a quantized oscillator jumps from one energy level to another. And he called this tiny packet a photon. And because they were observing that the energy that was carried by the photoelectrons was a function of frequency, he wrote that the energy of a photon is hf, related by the Planck's constant. Number two, he also said photons that he called give all its energy to an electron in the metal, and part of it is overcome in liberation, and the rest of it is taken away as its kinetic energy. So part of it is to eject the electron, and the other part is carried as its kinetic energy. Basically, it's speed. Is that what we were observing? Energies with the colors, the blue one will have more speed. The red one will have less speed because it had less energy to give. So he came up with this formula that says maximum kinetic energy carried by the electron, the photoelectron, is equal HF minus HF0. Put this in a box, put stars around it. This is very important. Where this is the energy of the photon, and this is called the work function. And what is the work function? Usually called phi. It is the minimum energy that the initial photon must have to liberate the photoelectron. If your incoming light only has energy equal to F0, it will have zero kinetic energy to carry it. Okay, when incident photon has energy HF0, then that implies its kinetic energy will be 0. Get it? Get it? Get it? Because it has just enough energy to eject it, but it can't go anywhere, it just sits there. So, how does this help us explain things? Well, that's the genius, because it explains what classical physics could not. Number one, photoelectrons will not be observed below cut-off frequency. So they called that particular frequency cut-off frequency, F0, regardless of the intensity of light. In this formula, the one I made you put in between stars, is there a place for intensity of light? So no matter how much you increase the intensity, if the frequency of your incoming light is less than the cutoff frequency, no photoelectrons will be ejected, regardless of how intense you make it. There's no spot for intensity in here, right? Number 2, maximum kinetic energy increases as you increase E gamma, incoming photon frequency. Number 3, kinetic energy max only depends on frequency of incident light and work function. Right? According to that formula you put in the stars, right? Kinetic energy max only depends on frequency. And number 4, this effect is instantaneous because there is a 1-to-1 interaction between photons and electrons. Once Einstein had said those things, they did a bunch of experimentation and they indeed found this. So experimental result, they found that. What does this graph tell you? That's 0. Everybody just stare at this graph for a second. It's a metal surface, and I am shining different lights on it. Okay, hold on. Let me go back to this. It's a metal surface. I'm shining different lights on it. Red. Any electrons emitted? Any yet? Any yet? I'm increasing its frequency, yes? Nothing, 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 nothing. Nothing, 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 nothing. Nothing, 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 nothing. Oh, the number of photons is less. Actually, hold on. Let me just do it this way. I won't show the photon because that's what they were observing, right? It's just light incident on a metal. Let these go away. Okay, intensity, not the number of photons. Make intensity big. Okay, nothing? Tell me when. So I'm increasing the frequency, going back to this. So keep this picture in mind, that one. Good? We're going to try to redraw that graph. Everybody got that picture in their head? Okay, we're going to go back here. Try to go slowly. Oh, it was in green. Oh, there it comes. Woohoo, something happened. I keep increasing it, and I'll go towards blue. What will happen? They're getting faster. Those ones are the old ones. Sorry, they should change color somehow, but do you see them getting faster and faster? From the previous one? Is that when you graphically show it, is that what that graph should look like? Nothing, 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 nothing. Suddenly, yes, and then the speed goes up and 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 up. Wonderful. And all because Einstein was able to write this simple formula. Such a pretty formula. Does it not deserve the 2 stars we have around it? I think it does. It's so pretty. And so he called this the cutoff frequency. For the metal, right? So this is the cutoff frequency for the particular metal that we are making an incident on. It'll be different for every metal that you have. And the work function is defined as HF0 for the metal itself. And another formula that you might want to write down is the lambda for the cutoff frequency, which is just HC over 5. What's the lambda corresponding to that? And it's simple. I can show you where it came from, so it's not like a magic box. We know speed equals lambda F0. We know this is going to be C over F0 equals lambda, or because we are now talking about quantum scale, multiply this with H, multiply this with H, what do you get? HC over 5. It's not like I plucked it out of thin air, it's the same formula.